Okay, summary questions for section 7.5. 7.5 is a section looking at stability, and the first question is explain why a bookcase with books on its top shelf only is less stable than if the books were on the bottom shelf. So in this situation we're just looking at centre of mass. We know that the higher the centre of mass, the easier an object is to topple, therefore the more unstable it is. If we put a lot of the mass of the object higher up, we're going to raise the centre of mass. We are raising the centre of mass, we're going to make it easier to topple. So that's the two things they want you to link together there. We raise the centre of mass, or the centre of gravity, by putting the bulk of the mass higher up on the object, and the higher the centre of mass, the easier it is to topple. Question 2. An empty wardrobe of weight 400 newtons has a square base of 0.8 metres by 0.8 metres and a height of 1.8 metres. A horizontal force is applied to the top edge of the wardrobe to make it tilt. Calculate the force needed to lift the wardrobe base off the floor along one side. Okay, so this is your sort of standard stability question that you might get. And what we're going to do, first of all, is draw ourselves a diagram. So, question 2. We've got a wardrobe. I'll try and make this big enough to see clearly on the video. And that wardrobe is sitting on the ground. Like that. Now that wardrobe will have a centre of mass, and the easiest way to draw the centre of mass accurately is to take the diagonals. So if we find the diagonal that way, the diagonal that way, this obviously works for a square. Here's our centre of mass. We're assuming in this circumstance a uniformly distributed mass, and the question gives us no reason not to suspect that's the case. The force of weight will then act from this point here, perpendicular to the, well, in this case we're on level ground, so perpendicular to the ground, always pointing downwards basically. We know that the base of this object is 0.8 metres. That's from there to there. I'm not sure if you can read 0.8 metres on the camera, I'll try and make it big next time. And the height from here to here is 1.8 metres. Okay. Now we consider the force. So this is the new bit that's acting. And the force is acting on the top corner of the bookcase, at the top here. And therefore the line of action of the force, which is very important in these type of questions, will work all the way along this line here. So there's the force, and this is the line of action of the force. Easy because it ends up being at the top. It's more complicated if the force ends up being halfway up the bookcase. We were given the weight of the bookcase as being 400 newtons. And the question tells us that the bookcase is pushed. Oh, we want to know what the force is that would make it lift. So, we've got all the bits we need in place. We need to first of all think of the clockwise moment. That's the one that involves our force. Then we can think of the anti-clockwise moment, and then we can put it all together. So let's look at the clockwise moment. So there's the clockwise version. And we get that the moment is equal to the force. We're looking to pivot there. We're looking for the point where this just starts to lift off. And we're looking at the moment supplied by this force being a value f. Don't know what that is yet because we're trying to decide what that is. Times the distance from the line of action to the force, to the pivot, sorry. So this is the line of action of the force, this is the pivot, the distance between them being 1.8. So that's the clockwise movement. That's everything that's trying to move it that way. Let's look at the anti-clockwise. So then we're going that way. No, I've just drawn clockwise. We're going that way. There we go. Now the anti-clockwise, the thing that's trying to turn it this way to try and resist that force, is obviously the weight of the bookcase, which we say is 400 newtons. And what is the distance of the line of action of that force to the pivot? Well, the line of action of that force is straight down the middle of the bookcase, and because it's evenly distributed, that will always be the case. And therefore the line of distance from the line of action to the pivot will be half the base, so in this case 0.4. Now we simply say that just at the point where it's about to tip, one will be equal to the other, so it's balanced. So up until then, this will be winning and it will be heavily down on the floor, and the floor will be taking the weight. There'll be a resultant force up, etc, etc. Right at the moment when pivot, these two balance. They balance perfectly, and then past the moment of pivot, the force becomes greater and it starts to move that way. So we're looking for the moment when this force, tipping this way, is balanced exactly by the force of weight that way. It's just before, if you increase F even slightly, you will now start to get a movement, a turning. So what we're looking for is the point where this is equal to this. And this is what we're used to seeing in moments. Sum of the clockwise equaling the sum of the anti-clockwise. Just get our head round why that's the case in these circumstances. And then we've got F times 1.8 is equal to 400 times 0.4, which means that 1.8F, if we write it nice and neatly, is equal to 160. We've got divide through by 1.8 and we get the force is equal to 160 divided by 1.8, which is 89 newtons. And that is the force at which we will be in perfect equilibrium just before we're about to turn. Okay, question 3. Question 3 says that we've got a vehicle of a wheelbase of 1.8 metres and centre of mass when unloaded, which is 0.8 metres from the ground. For part A, it says that the vehicle is tested for stability on an adjustable slope. Calculate the maximum angle of the slope to the horizontal if the vehicle is not to topple over. And if the vehicle carries a full load, this is part B, it will be less likely to topple over from the slope. Explain your answer. So, first part, move this up slightly. Question 3, draw a diagram. Always the same starting point. So we have a slope, and we are looking in this question for a specific point. We're looking for the point the vehicle is just about to go, just about to topple. And the best way to draw this on, obviously, originally, let's have a look at this, if I can try and simulate this with a ruler. Originally the slope's going to be about here, no problem for the car, no problem for the car. As it raises up, we're going to get a little bit less unstable, a little bit less stable, a little bit less stable, and we're going to get to a point, let's say it's here, where we're now at the point where the car is just at the moment when it's about to tip on. If we went any higher with the angle of the slope, it would start to slide or tip or something like that. So we're looking for that point here of tipple. Now we know from our stability understanding that that happens when the centre of mass, or the tipple happens when the centre of mass moves outside the base of the object. And the point, therefore, where it's just about to go, would be when the centre of mass is directly above the very edge of the base of the object. So how am I going to draw this on a diagram? It's very important to get a head around that because it helps us draw the diagram in a way that makes this much easier to answer. Well, imagine a centre of mass of an object here, and we'll draw that centre of mass line. We'll draw the weight force down there. I draw it that long just so that it clears the triangle. It doesn't give me problems with writing it on later, but that's not showing it's any large force for any reason. Then you draw your object perpendicular to the slope, but you start with the corner here, just where the slope intersects. Okay, so I try to make it look about like that. Now, depending on where you drew your centre of mass, it depends how realistic this is going to look. Mine's ended up looking quite narrow. Obviously a car would in real life be wider, but that doesn't make actually any difference at all. We just need to visualise what's going on, and this is the point where you can see quite clearly the centre of mass is directly above the corner of the base. Any more that way, centre of mass moves any more this way, it'll be outside the centre of outside the edge of the wheelbase, and we've got tipping. So this is the key and crucial point here. Now, we need to understand this angle here. This is the key bit. We want to know what that angle is. Interestingly, the mass doesn't really come into it at any point. The only reason the mass has an effect, which we'll come on to later, is because it moves the centre of mass. So it's not actually needed for the calculation of what angle will make it tip, as long as we know the height of the centre of mass. We do know the height of the centre of mass, so I'll just mark a line on my diagram here to say the height of the centre of mass is 0.8 metres. We know the width of the object, which I said this doesn't look very good for scale, but that's not an issue for me answering it. We know the width of this is 1.8 metres. So clearly I've made it look a bit wrong, but that doesn't matter. So, we're looking to try and find the angle theta. And to do so, we need to use the sides we know, these values here. Now, a little bit of trigonometry rules comes into play here, or angle sort of theory. If we extend this line down here, there are several angles on this diagram. Let's also drop a perpendicular to the slope here. There are several angles on this diagram which all are the same, and it's by knowing which ones these are that help us to understand this. So this angle is the same as theta. We have used this in other questions, so we have a theta here, and there's a reason for that, that if you cut a triangle in two with a perpendicular here, you end up making two triangles with the same angles, just smaller different sides. Also, from the situation we always get where we have two lines crossing, this angle is equal to this angle, and therefore if this is theta, this one here must also be theta. And then we have another situation which generally comes from a situation where you have two parallel lines, that we have this situation here. Okay, they're all names for these, but I'm not overly concerned about them, which means that this angle is also going to be the same as this angle. So there's lots of times where you'll find the same angle cropping up again and again in this diagram. Now how does that help us? Well, we can now look at this triangle I've made here. I hope you can see this on the diagram. We're getting into a very small part of a bigger diagram. So what I'll do is I'll just draw that out bigger here. Here's our triangle. So this line here is actually the weight. This line here is the slope, and this is a perpendicular to the slope. And it turns out that that angle there will tell us the answer. It will tell us what this angle here is. It's going to be the same. Why is this triangle useful, more useful to me than the other triangles? You could probably argue that this one here is just as useful, and if there's any physicists out there probably telling me that I'm going over the top with it, but still, I like this one, it works well for me in my head. This one I've got the dimensions of. Okay, I've got the dimensions of the height of this side here, which is this here, which from here is 0.8. And I know the distance here to here because it's half of the wheelbase. If the wheelbase is 1.8, then half will be 0.9. Now I've got a triangle where I know two sides and I want to know an angle. Simple trigonometry kicks in now. Now we can move from the more complicated to the pretty easy stuff. I've got, if this is the angle I want here, this becomes the opposite, this becomes the adjacent. So I'm going to be using tan. Okay, so we're now going to say then that tan theta, which is the angle we want to know, is equal to opposite, so that's 0.9 over adjacent, which is 0.8. And therefore, a little bit of rearranging, theta equals tan to the minus 1 of 0.9 over 0.8. And when you calculate that, you get 48 degrees. So at 48 degrees, the car will be at just that point where it's about to tip over. Okay, the next question from the book said that, as I recall it from what we said earlier, is that if the vehicle carries a full load of people, will it be more or less likely to topple over on the slope? So we have to think about basically what happens if we move this centre of mass. More people is going to move the centre of mass. Okay, now which way they're going to move? Well, I think this the book doesn't go into detail about this, and my first thought in my head was the centre of mass would be lower because we're all sitting down and your legs are all sit on the seats relatively low in the car. I often feel when you get in the car you feel like you're sitting quite low. But then the more I thought about it, and clearly then when I checked with the book and what they've done in their answers, it is true that actually it's probably going to raise it because the bulk of our body mass is actually above our waist. And all the extra space that was empty when the seats were empty is now filled with mass. It's actually going to raise the centre of mass. Not a hugely intuitive question. I think it's a little bit complicated, and hopefully you wouldn't get one like that in the exam. But even if you did, you could talk about the fact that it will move it up or down, and if the centre of mass is moved up, one thing, if the centre of mass is moved down, another thing, and hopefully you'd still get a mark. But in this circumstances, we're assuming that by putting a load of extra people in the car, we're going to fill up that empty void above the car seats that was once empty, raising the centre of mass. If we raise the centre of mass, and I'll draw another centre of mass on the picture for you to sort of see what I mean. If we raise the centre of mass, say to here, okay, and if we then imagine our new line coming down from that centre of mass, a line of action, it's now gone outside. It's now gone outside the wheelbase, which means the car would topple. That means for us then that if we raise the centre of mass, it will topple sooner, because clearly this point is going to meet the point where it's directly above at a lower angle. Because at this angle, which was fine before, it's already gone past it, which must mean that its angle where it was perfectly lined up directly above must have been smaller. So it will get to a smaller angle before it gets to the point of tipple, therefore it will be less stable, it will be easier to tip over. And that's because the centre of mass has been raised, which is very similar to question 1 when you think about it that way. And lastly, discuss whether or not a high-sided heavy goods lorry is more or less likely to be affected by strong side winds when it's fully loaded compared to when it's empty. Again, this is the same kind of question. The bulk of the mass of a lorry is actually very low down. And if you look at the figure 5 on page 102, they draw the centre of the mass very, very little, sort of halfway between the number plate and the front grille. Very, very low. And that's because lorries are designed to have a big empty void in the back to fill with stuff. So they put everything as low as they can to get a nice flat bed, what they call it, to put the stuff in the back. So even more than cars, lorries have a particularly low centre of mass. Therefore, any mass added to the back, anything you put in the back of a lorry, is going to start lifting the centre of mass. And as we've discussed, it's going to start meaning that it's easier to topple because of that. They're obviously, for a high-sided lorry, you're also going to have large forces because the point of action of force is going to be moved further and further away from the point of pivot as the sides get higher and higher and higher. So there are several factors going on, but the key thing for that question is that the centre of mass of the lorry, unladen, so with nothing in it, is very low. Everything you put in the back is going to raise the centre of mass. If the back is fully laden, completely full up, that's going to really raise the centre of mass. And we're talking on a high-sided lorry. I mean, I wouldn't be surprised, well over in excess of 50 centimetres, possibly even for some of the very high ones that you look at and think they don't look safe. It could possibly even be a metre higher, centre of mass, and so it's going to significantly change how it reacts to wind. And that is the end of the topics for the questions for topic 7.5. There's a lot of thinking and responding questions and wordy questions, not so much maths. Hopefully that helps you through that. And I'll see you on questions 7.6.